Hi there, welcome to this lecture series on matrix algebra. This is lecture 27, part 2, and the topic is Markov chains. So in this part of the lecture, we will go through one more examples using what we have learned about Markov chain to solve some problems. Let's get started. The example we'll be considering is on the wealth of a household across generations. So before we get into it, let me present this picture of Andrei Markov. And that's the guy, and it's his name that gives to this mathematical modeling of the problem. So we assume now wealth is passed on from generation to generation, and this process follows the following model. If parents are rich, then children, they have higher chances of being rich. And if parents are poor, children would have higher chances of being poor. And that's the assumption, and then we will later give a quantified number of exactly how much higher chance for each. And if that is the case, can we develop a mathematical model? Okay, so let's make our random variable. We call it capital X K. K would be the number of generations, starts from 0, 1, 2, 3 and goes on. And it can assume two values. When xk is 1, that means the kth generation of a household is poor. And when xk is 2, that means that generation is rich. So you want to have 2 and not have 1, right? And now we form the transition properties, that is, from one generation transitioning to the next one, how does the wealth, the situation change? So we assume the following. If parents are poor, then children have 1/10 of the probability of being rich, and therefore 9/10 of probability of still being poor. There is a little chance that they can be rich. Second, if parents are rich, then it's half-half, so a half probability of being poor and then a half probability of still being rich. So we can show in this drawing. So 1 is being poor and 2 is being rich. Let's say this is the parents' generation, and then this is the children's generation. So if the parents are poor, then you have a 0.9 probability of being poor as their child, and 0.1 probability of making it rich. And then for the rich parents, there's half probability of turning poor and the other half of remaining rich for the children. Okay, so we can now define our vector of probabilities. We call it Vk. Vk equals to, it's a vector, so this would be, the first element is the probability where xk is poor, and the second element is the probability that xk is 2, which means it's rich, so which is written here. So the kth generation is poor, the probability of that is the first element, and the second one is when the kth generation is rich. So we claim that these probabilities evolve according to this transition matrix, as we have talked about in the previous slides. So the matrix A would be exactly the probabilities of remaining rich or poor for each case. So we remember that it's 9/10 and 1/9 for poor, and the probability of their children's situation, and this will be for rich parents and the probability for the situation of their children. And then we can write that Vk equal A times Vk minus 1. Okay, after one generation, this probability for the parents and multiply on the left by the matrix A becomes the probability vector probability for the children. Okay, so let's fill in the details. We have this model VK equals A times VK minus 1. So what does that exactly mean? So VK here is the vector of probabilities. So that is probability that K's generation is poor and the probability that K's generation is rich. And then VK minus 1 is the same for K minus 1 generation. And then A times VK minus 1 will be the probability vector of this. So we can verify that this holds. Let's see. Probability K is poor. That is, for the children to remain poor, it's this state here. So it could come from two sources. One is a poor parent with 0.9 probability leading to the poor child. And then the second will be a rich parent, and with 0.5 probability, the kids become poor. So, and then if we look at this presentation, it's exactly what it says. So this row vector times this column in the product. So I'll have 9/10 times the probability K minus 1 is poor, which means is passing from here. So the probability in K minus 1 is poor is here, multiplied by this probability transition term here will contribute to one part here, and then the second part will be half times this, which is coming from here, times 0.5, and you will end up in here. Okay, and the second entry for probability K is rich will be here. If you end up here, and you see that you can come from a poor parents, but you make it rich with a small probability. That means this one times that, and then the second path will be in parents are rich, and then 0.5 probability you become rich, so it's a half times this one. So we are interested in the following question, that is, if the parents are poor at generation K equals 0, and then what is the probability after K generations that the household is rich? So we know we need to compute the powers of the K matrix, because V of K equals K a to the power K times V of 0. And V of 0 we know is 1, 0. And A is this matrix. So we need to find an A to the power K. And then this can be achieved by finding the eigenvalues and eigenvectors of A, as we have done many times. So we will find the characteristic polynomial by finding this determinant, fill in the detail, it's this one, and then computing the determinant, you get a polynomial of degree 2. And then you can use your quadratic formula to find the two eigenvalues. Here it's 1 and 2/5, and you work out your procedure of finding the corresponding eigenvectors, and you will find that W1 is 5, 1, and W2 is 1, -1. Okay, so we can diagonalize A using the matrix formed by the eigenvectors. So we call it P, which collects the two eigenvectors. So I have this matrix, and it's invertible, so we can find the inverse, and it will be that one. And then we know from previous study that we can diagonalize A by multiplying A on the left with P inverse and on the right with P, and we'll get a diagonal matrix with the eigenvalues on the diagonal. In this case then, we can write the power of a. A to the power k would be p, and the p inverse, and in between is the diagonal matrix to the power k. So we can fill in the numbers. So p is this one from here, and p inverse is here. We put it here, and d matrix to the power k, we just need to take a power on the diagonal. And for the 1, it's just 1, and for the 2/5 is this one. And then we see that we can write out vk, this vector here, for any k, which is a to the power k times v0, which is this expression here, which is a to the power k. We copy it down here, and then v0, we are assuming that initially the parents are poor, so it's 1, 0. So we are interested in the large time behavior. That is, after many, many generations, when k is very large, what do we have? So we are interested in the matrix d to the power k when k is very large, which is this one. So we see when k is very large, this number is strictly less than 1, 2/5. And as k goes to infinity, this goes to 0. So for large k, it's approximately 0. So we have approximately this matrix for d to the power k. And now let's put that in the a to the power k, which is that. And then we fill in the numbers. And here we fill in the large time behavior of d to the power k here. So we have this product, and we work it out, and we see that we have this matrix. So what it says that is when k goes to infinity, the a to the power k equals, let's say, this a bar matrix, which is this limit matrix here. 5/6, 1/6, 5/6, 1/6. We make the observation that, as we did in the previous example, that all the columns of A, they're equal. This column is the same as that column. And then we also observe that this is exactly the eigenvector W1 of the matrix A, with the corresponding eigenvalue lambda 1 equals 1 is corresponding to this one. So let's have the discussion. If initially the household is poor, that means V0 will be 1, 0. Then we can compute the VK as that. And in the limit, when K is large, this will be A bar times V0. So let's put in A bar and put in V0. So we work out this product, and we see that multiply it by 1, 0 will just give you the first column. So it's this one. And then if initially the household is rich, that means that V0 now is 0, 1, and we can carry out the same computation. Then it will be this matrix times 0, 1, which will give you the second column. But then the second column is the same as the first column. So the conclusion is that after many generations, the probability of being rich or poor doesn't really depend on the initial wealth. It is controlled by the eigenvector corresponds to the eigenvalue lambda equals 1, and that eigenvector is the large time behavior of the wealth asymptotically. So this is the end of this lecture. Next time we will look at another application of matrices in the graph and making sense of what the graph is telling us. Okay, so some exciting stuff coming. I hope you enjoyed this lecture, and I'll see you next time.